Hi everybody and welcome back. So for our next topic today, this one's important. This is the big one, Fundamental Theorem of Calculus. Today's goal is really to connect everything that we've talked about so far in Unit 4. If you remember, we started off learning how to use antidifferentiation to work backwards from a derivative function, going back to the original f of x function, and then we took a break from that stuff and we were focusing in on finding area under a given function's graph between the curve and the x-axis. Today is where we link those two things up together with the fundamental theorem of calculus. So to start, we're going to talk a little bit about units. So imagine we're finding the area of just some generic curve, represented in this case by this little squiggly graph. And to do it, I just draw one big rectangle. No, it's not going to be the best representation or estimation, but for the purposes of talking about its units, one big rectangle is pretty good. So I'm going to use that one big rectangle to approximate the area for that particular region. So if you recall in geometry, area is typically measured in squared units, so square inches, square feet, square centimeters, whatever it is. But in calculus, when I draw this region on a coordinate plane, I no longer just have dimensions measured in the same units because my dimensions have some kind of real-world context. So to come up with the accurate units for the area of that region, I have to take into account what are the units for my x variable and the units for my y variable. So to calculate the actual units, I need to multiply those two things together. For example, suppose we graph the function of v of t. So let's say that this squiggly graph represents the graph of the function v of t, or velocity. So it's the velocity of an object, and the units for velocity are being measured in feet per second. Well, that would mean that the y direction, so when I have a rectangle that are 4 units tall in this direction, the units of that dimension are feet per second. And then imagine that the input variable for v of t, or t, so that's the t-axis here, this is v of t axis here. So that's measuring time, and that's being measured in seconds. So that would mean instead of this just being 5 units wide in this dimension, that would be measuring the number of seconds that have passed. Well, if that's the case, when I go to calculate the area of that region, not only do I get a real-world number, but the units now take on a real-world meaning. So if I simply multiply feet per seconds by the other dimension, seconds, these cancel out, and what we're left with is some number of feet. So in this case, when I take the integral of this velocity equation, or I find the area under that velocity equation, whatever this number is, the units of this thing, it's some number of feet, which is a bit of a breakthrough for us. And this is kind of where we lay the groundwork for the connection between our antidifferentiation and our area problems. So the idea here is these things are interconnected by the concept of the fundamental theorem of calculus. So if you remember back to the beginning of the year, I told you guys that this course focused on two main topics: differential calculus and integral calculus. Those two might seem unrelated, but again, differential calculus is the way that quantities change. Integral calculus is actually worried about the summation of those changes. So there is a really important connection that was discovered independently by both of our big calc guys, Newton and Leibniz. That connection is the fundamental theorem of calculus. So essentially, this theorem states that differentiation and definite integration, so finding the area under a curve, represent inverse operations of one another. So to represent or to visualize this, I want you to take a look at this graphic here. This is a pretty good explanation of what exactly is going on. So in the differential calculus world, if you think back to the beginning of the year, we began with an estimation process. Our end goal was to be able to quantify the change that a curve has at a given point. And the way that we started that was finding the slope through two endpoints. So from an a f of a to a b f of b, I found the slope through those two. And so another way of thinking about that is I had a change in y divided by a change in x. So that's the slope. So division was the main focus there. So I started with that estimation process, and then through the limit process, I moved that window closer and closer between the 2 points, and so that approximation became the real thing. So for differential calculus, it was dividing the quantities of the change of y and the change of x. Well, the inverse of division is multiplication. So now if I take that curve and I look at that same window of time, that change in x versus that change in y, again, with area problems, we started with an estimation process. I took a region under a curve and I used rectangles to approximate that area. Well, now just imagine that I do a really bad job estimating and I just use that one rectangle, like I see here. That area of that rectangle is now represented by the change in x by the change, or multiplied by the change in y, or the inverse of what we just did for slope. So this is a very broad interpretation of this, but we can kind of connect the dots here and say that the opposite, or excuse me, the inverse of slope is actually the area of this curve, or the inverse of delta y divided by delta x is delta y times delta x. And now through the limit process, again, we just saw in the last two sections, the idea of us being able to calculate the exact area under this curve by simply taking the limit of those Riemann sums. And so now what we're going to learn is how to represent that or evaluate that process through this new notation with that definite integration. So both of these kind of went through similar process. We started with an estimation, we refined it, we applied calculus through the use of limits, and that turned it into the real deal, the real slope of the tangent line or the curve, or the real area under that curve. So the connection between the two is the idea that taking the change of a function is actually the opposite of the area under that function. So that's the big connection here. So what the fundamental theorem of calculus says, this is actually the definition of the fundamental theorem of calculus. If a function f is continuous on the closed interval from a to b, and capital F is the antiderivative of f on the interval a to b, then the integral from a to b of f of x dx is actually equal to the antiderivative f evaluated at b minus the antiderivative of f evaluated at a. Or, to put this in a little simpler terms, another variation, of this is if I take the integral from a to b of f prime of x dx, that is equal to my original function f of b minus f of a. And that's kind of a much easier way for us to understand this and wrap our heads around this. The idea that, again, these integrals, these definite integrals, we translated these last section from the sigma notation problems, so the summations, into this new notation. But if we go back to the sigmas just for a moment, this is really saying the sum of all the change that the function f of x goes under over the interval from a to b is really just equal to what is the value of of f at the end of the interval minus what is the value of f at the beginning of the interval. Easiest way to think about this, let's say that you're a cashier and you work at a grocery store, at Food Line. And at the beginning of the beginning of your shift, you have $200 in your drawer. At the end of your shift, you have $1,000 in your drawer. Well, the summation of all the change can be quickly, easily found if you know your starting and end values. We just subtract those two. But now what we're able to do is say that this, which up until this point was simply representing the area under the curve of f prime, now that area under that curve can be calculated by going back to the antiderivative of the function I'm starting with and finding those 2 points and just subtracting them. And that is kind of a big deal. Now we don't have to do the limit process anymore. Now we don't have to worry about making geometric shapes or anything like this. If I can find the antiderivative of my function, I can use the fundamental theorem of calculus to tell me what the area under that curve really is. And now, more importantly, we have this real-world application or this real-world understanding of what that area means to us. And that is this total amount of change that we see occurring to a given function. So let's continue putting all this together. So again, the most powerful application of the fundamental theorem of calculus is using it to help us find the area of a curve. We can do this so quickly and easily, and I'm going to show you with some examples here in a minute. So because we now have that new method to evaluate a definite integral, we don't have to worry about needing to take that limit of a Riemann sum. We are done with those. You guys don't ever have to take the limit of a Riemann sum again after today because of the fundamental theorem of calculus. So from now on, if you are ever asked to find the area under a curve or interpret the area under a curve, whatever it is, if you're trying to evaluate the area under a curve, we will be using this new method to help us solve for that value. And it's so much better, so much faster. So let's try some. So first one here, I want to take the integral from 1 to 2 of the function x squared minus 3 dx. So again, in the simplest terms, this integral is equal to some number, and if I want to evaluate that number, I have to understand that it's really equal to the area under the function x squared minus 3 from 1 to 2. So I tried sketching this once, had to delete the video because of how bad I drew it. So let's use Desmos. So here's my function x squared minus 3. I'm going to put a domain restriction on this guy from 1 to 2, okay? So that's the only part of the curve that I see. But again, that region is partially below x-axis, the x-axis, and then partially above. So let's see, x equals 1. Let's give this, let's polish this guy up a little bit. So we're going to say f of x equals, and we're going to go from, let's see, y equals -2 to 0, and then x equals 2 from 0 to 1, okay? Just to paint the full picture of this graph. And then let's shade this guy in. So we're going to go from, I want f of x, y is greater than f of x. Let's keep it to 0. Okay, there we go. And then same thing on the other side. 0 is f of x. Oops. There we go. All right, let me change that one to green. So here is our region, okay? Now, again, in the middle of this is my parabola. I'm only looking at part of it, though. So that first region, the gray region there, is actually going to be a negative quantity because it's sitting below the x-axis. The green will be positive because it's above. But our integral, the total value, should be those two things combined, okay? So we don't have to go through the limit process. We can estimate this. They kind of look like triangles, so we could give rough estimates for them, but we don't even need to worry about any of that anymore. This fundamental theorem of calculus process will do all of that for us. So the way this works, notationally, I'm going to first find the antiderivative of this guy. So I'm going to turn this into, I'm going to use brackets. So inside of the brackets are going to go the antiderivative of this function. So indefinite integral, same language. So x squared, using the power rule of integration, will become x cubed over 3. Again, this is where we have to go back and review some of our rules a little bit. And then -3 will turn into -3x. Now, we make a switch here notationally, so we have to use the fundamental theorem of calculus rule, which says the integral of f of x from a to b is equal to capital F of b minus capital F of a. So these are actually going to turn into numbers that we subtract. So notationally, how I want you guys to express this is after we've found our antiderivative, we're going to put our a and b values on the side of this bracket. That will be your trigger, your tool to help you remember. Now I have to plug these in. So now I'm going to find my f of b. So in parentheses, this is where f of b will go. So I'm just going to set it up, and then we'll evaluate. So 2 goes in, that will give me 8/3 minus 3 times 2 is 6. So we'll simplify that in a minute, but that's all of my f of b quantity. So that's the value of the function, or the function's antiderivative at the end of the interval, and then minus the function's antiderivative's value at the beginning of the interval. So now we plug a in. So that would be 1/3 minus 3. So that is our f of a. So now all I have to do is do all the math, clean all this up. This is just addition and subtraction. So I'll distribute the negative here. Then it's just combining terms. So 8/3 minus 1/3 would give me 7/3. Negative 6 plus 3 would give me negative 3. So this would turn into minus 9/3, or a final value of negative 2/3. So negative 2/3 is the total signed area between this curve and the x-axis, which, if you go back to Desmos, it makes sense that the final answer is negative. There is a bigger region below the x-axis than there is above the x-axis. But that is our final answer. This negative plus that positive actually comes out to be negative 2/3, which to me, and anyone who's any bit of a math nerd, is pretty wild, because we just found a finite value for a non-geometric region. So that region has no kind of actual geometric shape to it. There's no known formula to calculate the area of that. The only way that it's possible to do that is with calculus, either with the limit of our Riemann sums, or now we can do it quickly and easily with our fundamental theorem of calculus. So again, what we just did here, replaces all those big, ugly summation formulas and the limits and stuff. That's why this is so powerful, is it just makes life so much easier being able to do this as opposed to those limits. All right, now let's try another one. So this one, integral from 1 to 4 of 3 square roots of x. So let's take a look at what that graph looks like. So f of x equals square root of x. Okay, and this time we're going to go from 0 to 4. Excuse me, 1 to 4. Okay, so let's look at x equals 1. And let's go from 0 up to f of x. And then x equals 4, same thing. Oops. Okay, so there's my region. Okay, and then let's do y is less than f of x. And use that same interval. Oops, actually, no, we'll go from 1 to 4. All right, there we go. So that is my region. So now for this one, the entire region is contained above the x-axis, so this one's going to be a positive value for sure. But just to help you guys visualize what the region looks like, that is the area that we are trying to calculate. So for this one, now anytime that we have these coefficients inside, to make things easier, we are actually allowed to move those out in front. That's just like saying, if I had sigma of 2x, or let's say 2i, then that 2 is allowed to move out in front. It's essentially what we did with our delta x's in those summation problems. So we're going to move that out in front and leave it alone for right now, because a lot of times what ends up happening is those extra coefficients inside get in the way or make things more difficult when finding that antiderivative. Okay? So now we are going to find our antiderivative. So I would rewrite this as x to the 1/2, just like we would rewrite radicals as fractional exponents to take the derivative. It also makes it easier for antiderivatives. And we've done that in the past, so this one would become x to the 3/2 power. Remember, we add 1, divide by the new power, but remember, dividing by 3/2 is like multiplying by its reciprocal of 2/3. And then just like before, my a and b values will go out here at the end. So at this point, it's really up to you. I can either plug in b and a and then multiply the final result by 3, or we can go ahead and send the 3 in, simplify it, and then pass our a and b values into it. In this case, since the 3's would cancel, that would be the easiest way to do this. Go ahead and distribute the 3 and simplify everything, and now we can go ahead and evaluate. So for my f of b part, when I plug 4 in, fractional exponents are tricky. Remember, 4 matches up with the root, so I'm going to square root that, so it becomes 2, and then 2 cubed turns into 8. So I get 2 times 8 for the first value, and then minus, when I pass 1 in, 1 to any power is just 1, so this is 2 times 1. Or 16 minus 2, or 14. And for our next one, this one says the integral from 0 to pi over 4 of secant squared x dx. Again, that's asking for what is the area between the x-axis and the curve secant squared x on the interval 0 to pi over 4. So if we take a look at this one graphically, this is what this region looks like. So here we have secant x. Remember, it's like the weird parabola-shaped looking curves, not actually parabolas, but same kind of idea. And then from 0 to pi over 4, so we have an all positive region, so we should get a positive answer for this guy. So again, process is finding the antiderivative. So if you remember, secant squared is the derivative of tangent of x, and then we'll put our interval out here. F of b would be tangent of pi over 4, minus f of a would be tangent of 0. Tangent of pi over 4, that would be like asking on the unit circle, what is the slope at the angle of pi over 4, or what's the y coordinate over the x coordinate? It's the same coordinate for both, so my slope is 1. And then tangent of 0, that's like saying what is the slope at 0, which is 0. So we get a final answer here of 1. And so another way of thinking about this, if we go back to Desmos here, so again, this is our region, and what we just figured out, which I find really fascinating and just odd, is that weirdly shaped region, again, it's not a polygon because this curve doesn't really, we wouldn't qualify it as having sides, unless you think of it as infinitely many sides up top there, but that weirdly bounded region has the same area as a 1 by 1 square. So what's missing here from the square is actually accounted for in this extra piece up top. So it's just very strange and odd to think that these predetermined or like nicely defined polygons, their areas can match some of these really weird shapes. It's really fascinating to me to think about. So again, that is what these definite integrals now become and how we can evaluate them quickly and easily using the fundamental theorem of calculus. So now what we're going to use is use some of the properties that we learned about integrals along with the fundamental theorem of calculus. So for this guy, so the integral from 0 to 2 of the absolute value of 2x minus 1 dx. Now, we have the graph of this guy over here, and I'll get to that in a second. But the issue with this function is the function that's defined inside the integral to begin with does not have a integration rule or an antiderivative rule. If you go back and look at the list of antiderivative rules that we used back in 4.1, there is no absolute value function listed there, and that's because absolute values are piecewise functions. They are a set of pieces of different functions, opposite functions, paired together to make one continuous graph. The issue with that is I can't just do one integral to solve this problem. Now, looking at the graph, the function inside is a linear function, which means this region is always going to be triangles or trapezoids or some kind of geometric shape. So we can use geometry here to solve this guy pretty quickly and easily. This guy has an x-intercept or vertex at x equals 1/2. So that means this mini triangle has dimensions 1/2 by 1. So its area is 1/4. And then this big guy has dimensions of 1.5 by 3. So its area is, 4.5, 2.25, so 9/4. So combined, the total area is 10/4 or 2.5. Now, we can figure that out using geometry, but we can still use calculus and actual doing the math to evaluate this. The way we go about doing that is we treat this like the piecewise function. So remember, the way that we go from absolute value to piecewise is this function is equal to itself when its value is positive. So that is true when x is greater than or equal to 1/2. and it's equal to the opposite of itself when the output is negative, and that would occur when x is less than 1/2. So knowing that, what we have to do is now break this interval up into two intervals. So this goes back to the property that says the area from a to b of f of x dx is equal to the area from a to c of f of x dx plus the area from c to b of f of x dx for some value of x in the middle of the interval. So piece plus piece equals the whole thing. So that's what we're going to have to do here. But this is slightly different because now when we break it apart, the function inside is going to change. We're going to use each appropriate piece for that integral, and then we can actually do the fundamental theorem from both. So this would become the integral from 0 to 1/2 of negative, or the opposite of 2x minus 1 dx, plus the integral from 1/2 to 2 of the original 2x minus 1 dx. So now this just becomes two fundamental theorem problems. Now for the first guy, I'm going to distribute this negative inside, so I'm going to get rid of it out in front. That way I could just evaluate or integrate each term. So for the first one, we would get the integral of negative 2x would be negative x squared. Integral of 1 would be plus x from 0 to 1/2. And then we'll add to that the results from this guy. So 2x just becomes positive x squared, and that would be minus x from 1/2 to 2. So we'll do f of b minus f of a for each of these guys separately, and then just put all the pieces together. So f of b would be 1/2 squared is 1/4, so this is negative 1/4 plus 1/2, that's our f of b, minus f of 0 would be 0, plus f of b for the second interval would give me, 2 squared would be 4, minus 2, so that's my f of b, and then minus 1/2 squared is 1/4, minus 1/2. So the 0 we don't need to worry about anymore. Negative 1/4 plus 1/2, that is positive 1/4. 4 minus 2 is 2. And then here, let's distribute the negative, so this becomes negative and positive. So 1/2 minus 1/4 again is 1/4. So 1/4 plus 2 is 2.5, or what we got by geometry. So you guys can see that the math still works, but anytime that we're working with an absolute value function or even a piecewise function, if that were the case to be like an existing piecewise, we would not be able to use just one integral and one interval to actually evaluate that area. We always have to break it up into pieces. And if you really think about it, we did that as well when we did the geometry. The shape that, or the region that's created here, is not just one polygon, it's two triangles. So we had to break it up into the first one from 0 to 1/2, find that area, then from 1/2 to 2, find that area, and then combine them. So we're still using that this integral property, whether we do it with the fundamental theorem or if we do it by geometry. So that's a really important one for us to keep in mind. All right, so now we're just going to try a couple other oddball problems, just other ways that these guys can show up. Looks like I've got a little typo here. This is supposed to say dt, not dx. Sorry about that. Okay, so just getting used to some of the old integration rules that we haven't seen in a little while since that first section. So for this one, I want the area from 1 to 4 of the function t squared minus e to the t plus 2 over t dt. So let's integrate t squared, that's just a power rule, so this becomes t cubed over 3. E to the t, remember that integral is just e to the t, or e to the x, same idea. But then remember, for a constant over t, remember if I rewrote that as t to the negative first, which some of you may be tempted to do, thinking that this is a power rule, if I tried to apply the power rule to this, I would get 2t to the 0 divided by 0, and that's a no-no. And that's because power rule only works when our original exponent is anything but negative 1. Negative 1 is the only power that I can start with that I'm not allowed to use the power rule for. And that's because that's not a power rule. This is the natural log rule. Remember that the derivative of natural log of x turns into 1 over x, or natural log of t turns into 1 over t. So this has that form that this is going to turn into 2 natural log but this has to be absolute value of t. Again, that's an issue with domain. The original function has a domain of all values except 0, so we need its antiderivative to match that domain. So those absolute value bars allow us to use negative inputs. The only thing that we still can't use is 0. And then we're going to go from 1 to 4. So plugging 4 in, this would become 64 thirds minus e to the 4th plus 2 natural logs of 4. Now, once I evaluate it and I plug a value in, the absolute value bars can be dropped if they're not necessary. So if we plug a positive in, it's fine. If we plug a negative in, we change it to a positive, and then those bars drop out. But when we're writing the generic version with variables, we have to keep those absolute value bars in there. And then minus, plugging 1 in, we would get 1/3 minus e to the 1st, and then plus 2 natural logs of 1. So if I clean this up, let's distribute this negative plus negative. 64 thirds minus 1/3 would be 63 thirds, or 21. Then I've got a minus e to the 4th plus e. But then for these natural logs, natural log of 1, if you remember, that is actually just 0, so that guy disappears. So we just have plus 2 natural logs of 4. And if you really wanted to be efficient with what we're writing, we could use a logarithmic property that says these powers can actually go back up top. So I don't need to write this as 2 natural log of 4. I could actually make it natural log of 4 squared, or 16. So that is the simplest way to write that answer. And I know that seems like gibberish, but sometimes it's best to leave it in the exact form rather than getting decimal values. All right, now for the second one, this one's a little tricky. So this one, we're not actually trying to find the value of the integral. We know the value of this integral is equal to negative 36. What we want to answer is, what would the value of k have to be for this to be true? So that's a little tricky for us. So what we do in this case is we're going to do all of the exact same math that we just did, but instead of plugging a number in to the antiderivative where k is, we're going to plug k in. So changing that one value to a variable does not change the overall process. What changes is the end result and how we go about finishing the problem. But I would still integrate this guy like normal. So the integral of 2y, I want a different color, let's do purple. Integral of 2y would be y squared. Integral of negative 12 will be negative 12y. And we're going to go from 0 to k. But again, this result is equal to negative 36 the whole time. So now I'm going to do fundamental theorem of calculus. K goes in. So that would produce k squared minus 12k. And then minus 0 goes in. Well, that produces 0. And again, that answer has to be equal to negative 36. So all this does is creates an equation that depends on the value of k, which is perfect because k's value is what I'm searching for. So this is simply a quadratic function, or quadratic equation, excuse me. So I'm going to, I don't need the minus 0 anymore. I'm going to bring the 36 over, so we get k squared minus 12k plus 36 equals 0. I can factor this guy. This factors to be k minus 6 times k minus 6, or k minus 6 squared. So our solution, or our value of k, is positive 6. So now what that means is if I was to redo this problem but with a 6 in there instead of k, I know the final answer should end up being 6. Changing this to a number instead of k does not change the antiderivative. It just means on this line, if I were to pick up from there and do 0 to 6, when I plug 6 in, I would get 36 minus 72 minus 0, or negative 36. So it's just an abstract way of us asking you guys to show that you understand the fundamental theorem of calculus and how to use it, but then we can also apply it to solve some of these kind of crazier looking questions. So when you come across a k problem like this or something of this variety, don't freak out or overthink it. Just do the math that you know how to do and then use that result to help us solve the equation. All right, now we're going to take a look at an application. So we know the fundamental theorem of calculus now. So the rest of this section is just a look at different ways to taking that concept and applying it or interpreting it to different scenarios, different things. So the first of those is called the average value theorem. So the average value theorem says that if f is integrable on the closed interval from a to b, then the average value of that function f is 1 over b minus a multiplied by the integral from a to b of f of x dx. So I feel like the best way to explain this is just thinking of the term average and what you guys already know. So if I give you the height of 10 different students and ask you for the average or the mean of that data set, well, the rule is you add up all of those values and then you divide by, add up all of those data values and then you divide by how many of those data values you have. Well, that is essentially what we're doing here, just kind of in a roundabout way. So the idea is average value, we need a total divided by some kind of quantity or relative quantity. Remember that this integral really is a sum of y values. So this idea is the first part here. Let me erase my writing here to reword it here. So recall that the other version of this, our Riemann sum, says that this is really the sum of our heights, so f of c sub I, multiplied by our delta x, okay? So our height, you guys can see a direct correlation, our f of x is in here, but remember that that delta x is really, let me rewrite it a second time. Remember the formula for that guy is that b minus a over n. Well, if I were to pull that guy out in front, we end up with b minus a over n times the sum of all those heights. So again, this notation is really like the total of all those y values, okay? So if I want the total of my y values to then be divided by the number of them that I have, our n value, I got to get rid of this b minus a out in front, which is why we multiply by 1 over b minus a. So when we do that, essentially what happens is we're canceling these out, and we're ended up taking the total of all these y values divided by n, which is like the average value of all of those y values. So it's kind of a roundabout way, but in doing so, it allows us to take a function with a real-world meaning and then actually calculate the average value for that function at any value of x within that interval. And that's a pretty helpful thing in a lot of real-world scenarios, a lot of physics-related and a lot of economics situations. So to use it, though, it's pretty straightforward. Whenever I ask you for the average value of some function from now on, when you hear that phrasing, that function is what is going to go into the integral. And for a problem like this, it's pretty straightforward, so it's not that confusing. But when we look at the next guy, you're going to see where it can get a little tricky. So, but that's the rule. Average value of a function, that function must go into the integral. So if I set up my 1 over b minus a, my interval is going from 1 to 4. So 1 over b minus a would produce 1/3. So I'm going to take 1/3 multiplied by the integral from 1 to 4 of 3x squared minus 2x dx. So that would give me 1/3 times, so that 1/3 is just going to hang out in front for right now. So 1/3 times my integral of 3x squared, that would turn into x cubed. Integral of 2x would turn into x squared from 1 to 4. So I'm going to take 1/3 times the result of f of b would produce 4 cubed is 64 minus 4 squared is 16 minus f of a, that would produce 1 minus 1, so 0. So we end up with 1/3 times, sorry, 1/3 times 64 minus 16, that gives me 48. 1/3 times 48 is 16. So what that is telling us, let's go to Desmos here. So let's look at f of x equals 3x squared minus 2x. We're going to go on the interval from 1 to 4. So what that is telling us is, now, this is a part where it's a little difficult sometimes to wrap our head around this, and that's because we're dealing with a lot of concepts or applications of infinity. So hypothetically speaking, on that part of the curve, there is an infinite number of points that all have different y values, and each one is used with a weight or an amount of importance that is really close to 0. So if you think about the span or the interval that each different value of x is used, they're only used one time. We see that because the curve doesn't repeat itself up and down. So each one carries a weight that's infinitesimally small, or 0. So if we had a value that was used a whole bunch of times, then its weight or importance would be amplified by the number of times it was used. But because of that, if I tried to add up all of those different y values, it's theoretically impossible because there's an infinite number of them. But through the use of calculus, we can translate that process using the Riemann sum that I showed you guys earlier. By using the integral of this function, we are kind of taking the area, which is all those y values multiplied by the other dimension, and then dividing out that dimension. So that b minus a is that x dimension, or delta x, but we're canceling it out by doing the 1 over b minus a. So that kind of leaves us with the total of the y's, but then we're also going to be dividing it by that n, which is how we average this out. So what our result here is saying is the average value of this function anywhere on this interval is y equals 16. So you can see here, some people would believe or want to think that, oh, well, it would just be the average between the endpoints. So I'm going from f of 1 was 1 to f of 4 is 48 minus 8, 40. So some people would just say, oh, well, it's 20.5. It's right here in the middle. Well, that's the midpoint between those, but it's not the average. So what we have to account for is how quickly or slowly the y values are changing. So for example, looking here at the beginning of the interval, the graph is not as steep as it is at the end, which means the graph spends more time. When we think of time, we're talking about our x interval. It does not increase to those upper values above 16 as quickly as it does in the end part of the interval. So at the early part, down here at x equals 1, x equals 2, around that time in the part of the interval, we're not growing as quickly, so we're staying in those smaller y values a little bit longer, or for a larger chunk of the interval. But then at the end, when the graph is getting very steep, we're increasing towards those higher values faster, so we're not spending as much hypothetical time in those types of y values. So if we had a graph that was really, really steep the whole time, then you would see the average value get pulled up. But because this graph is less steep at the beginning, it's like having smaller y values pulling that average down. So that's the idea of this mean or average value of these y values. So it's not always going to occur right in the middle of my endpoints. It's really all about the shape of the curve and where we spend the majority of our time, or what kind of y values the majority of the interval uses. So because we have smaller y values for more of the interval, we pull that average down. But that is the idea of the average value theorem. It's a way of calculating the average or mean value of a function across a given interval. So an application of where this is beneficial or helpful to us is vertical motion. So this says a ball is fired from a cannon, and its position can be modeled by the function s of t equals negative 16t squared plus 48t plus 10. We want to find the average velocity of the projectile over the interval 1 to 3 using two different methods. So there are two different ways for this particular problem. One uses differential calculus, one uses integral calculus. So the first one, let's do differential first because that's an older one and we've actually seen this before. So recall that velocity equals the change in position, okay? Now the velocity function, if I wanted to find that equation, would be the instantaneous rate of change for that position function. But this is asking for average velocity. So when I estimate or find the average velocity, that's like saying what is the average rate of change of s of t? Well, that's like saying the slope of the secant line. So if I had the graph of s of t and I pick 2 points on my interval from 1 to 3, and I found the slope of that line, that would represent the average velocity or an approximation, the average rate of change of position. So that's how we go about this with differential calculus. So if you recall, in this case, we're going to say average velocity is equal to the change in position over change in time. So that is like saying s of 3 minus s of 1 over 3 minus 1. Or another way of thinking about it is, what was the position at the beginning of the interval? What was the position at the end of the interval? And then I divide it by how much time has passed. So s of 3, so we actually have to do some substitution here. So let's do a little bit of brain math. So 3 squared is 9 times negative 16 is negative 144. Plus 48 times 3 is also positive 144, plus 10, so those cancel. So our average velo is s of 3 would be 10. So that's the position of the cannonball at the end of the interval. So it must be 10 units above the ground. And then at 1, if I plug 1 in there, I get negative 16 plus 48 plus 10. So 58 minus 16 is 42. So again, what that's saying is the cannonball was fired, and after 1 second, it had a height of 42 feet above the ground. And after 3 seconds, it has a height of 10 feet above the ground. So cannonball must be on average going down during this interval. And it took us 2 seconds, or from 3 to 1, to have those different positions. So we end up with negative 32 over 2, or negative 16 feet per second. So that is the average velocity during that interval. So on average, we're saying that the cannonball is traveling downwards 16 feet per second. That is not the instantaneous rate of change. To answer that, we would have to pick one value of x and use the velocity function. But in this case, all we're asking for is what is the average rate of change across the interval. Okay, so that's differential calculus. Again, that should be a review. The new way of doing it for integral calculus, this is really notation heavy. So again, a minute ago, I told you guys that the language of the problems tells us what to write. So when I ask you for the average of a quantity, that quantity in particular is the one that must go inside of our integral. So we still set up 1 over b minus a, so that's 1 over 3 minus 1. And that will be multiplied by the integral from 1 to 3 of the velocity function. So we can use notation inside of these. Just like I could use notation in derivative problems, I can use notation or function names inside of an integral. It does not change the process. Okay, it still represents or means the same thing. So now what we're going to do is integrate this guy. So again, I don't have an equation for v of t. I could find one, but it's unnecessary. Because I know if I take the derivative of position and find velocity, if I take the velocity equation and integrate it, I'm just going to go right back to the position function anyways. So this is actually an easier problem if I just simply use the name of it. So I know that the antiderivative, or the function that came before velocity, is position, s of t. So now if I apply the fundamental theorem of calculus with this setup, I would have 1/2 times s of 3, that's kind of my f of b, minus s of 1, that would be like my f of a. Well, if you really look at it, this and that are equivalent to each other. They're the same thing. I'm just writing the division as a separate coefficient out in front, but I could really set this up as s of 3 minus s of 1 over 3 minus 1, or 2. These are equivalent problems. This is actually a direct link between the differential side and the integral side. It's just a matter of what function we're starting with. With differential calculus, to find average velocity, because it's a process moving forward, we're using the first guy to estimate that value of going forward. But with integral calculus, it's a process going backwards. So because I want the average velocity, that's the quantity I'm starting with. And because it's integrals, I have to go back and use the value of the original function position to come up with it through that fundamental theorem of calculus. So in both situations, we end up with negative 16 feet per second. So again, another way of thinking about that, let's graph this position function. Now again, I have to use x's to graph this guy in Desmos, but again, same idea. So we got negative 16x squared plus 48x plus 10. Let me just double check. Okay. So again, this graph represents the position of the object, of the cannonball, and I want to go on an interval from 1 to 3. Okay. So at the beginning of the interval, we had put my equals in here, we have a position of 42. At the end, I have a position of 10. But if you notice, looking at the position graph, you can tell that the cannonball was not actually decreasing the entire time. It was actually increasing for a little bit, then we reached its maximum, and then it began to decrease again. But overall, the average velocity across that whole interval really is the slope through that tangent, or excuse me, through that secant line. So the average slope would be that negative 16 that we found. So that's looking at the position graph. Now, if I graph the derivative function, or again, that would be our velocity. If I just look at that guy, we go from a velocity of positive 16 at the beginning of the interval to the very end has a slope, or an instantaneous rate of change, of negative 48. Well, now, because this is the velocity, if I had that equation and we did that process over again and used or found the average value of the actual velocity equation, you guys can see that negative 16, that actually is right in the middle of these two. But if you think back to the difference between this derivative equation, or this function that we're finding the average value of, and the curve we found before, the curve was changing its rate of change through the interval. And again, the average was dragged down to the slower part because that's where the majority of the slopes spent time at. This guy has the same rate of change in the entire graph, or this particular curve has the same slope. So in that case, the average value actually will end up being right in the middle because it's moving at the same pace the whole time. So just a couple different ways to calculate or interpret this average value. All right, let's take a look at one more here. So for this one, instead of giving you a function, I've given you the graph of some function, and this one is clearly a piecewise. We've got a bunch of different line segments put together, but I still want the same end result. I want the average value of f on the interval from negative 4 to 4. So again, in this case, we're really considering, of all the different y values, what is the average one? And again, the idea of steepness of our graph. So the steeper that a graph is, the quicker it passes through that set of y values on a smaller interval. So it's going to be, the average is going to be affected by that. The slower it moves through, or the less steep, then it's going to kind of balance out for that. Now, because these are line segments, for each one of these line segments, the average value would actually be right in the middle of it. But again, if these were curves, it still kind of practices that same idea of slow moving versus quickly moving through a given interval. But for this one, so if I set this up, I want the average value over the interval negative 4 to 4, so that's a total of 8 units wide, so 1/8 out in front, from negative 4 to 4 of our function f of x. Now, to evaluate this, again, whenever we have a definite integral now, technically we always have a handful of options. So option 1 take the limit of some Riemann sum. Not going to want to do that, but you technically have that choice. Option 2, we can use geometry to evaluate the area between the x-axis and the curve if we already have the graph and we know that the function creates basic geometric shapes. Or option 3 now is that fundamental theorem of calculus. So in this case, we don't really have the ability to choose 1 or 3 because we don't have equations for all these. Now they're line segments, so if you really wanted to, you could come up with the equations, but it's not necessary. So in this case, we're going to go with option number 2. We're just going to find the geometric area of all of these shapes. Now remember though, regions that sit above the x-axis are positive signed area, regions below the x-axis are negative, so we do have to account for that. So even though there are 5 line segments, we can actually break this into several shapes. So my first triangle has a base of 2 and a height of 1. So that area would be positive 1. So that's the first piece of this puzzle. So we got 1 plus. And then we have our second triangle that is completely contained in the bottom region, so negative. So it has a base of 3 units and a height of 2. So its area would be negative 3. So that's the second area. And then this last part, I'm going to split into 2 pieces. So first I have a triangle, right triangle here, 2 by 2. So its area would be positive 2. And then the last guy is trapezoid. And really, we could break this into 2 pieces as well. Little triangle would have an area 1 by 1. So that would be an area of 0.5. And then the bottom guy is just a 1 by 1 square, so plus 1. So that is my all the area of the pieces. So if I combine all of those, again, I still have the 1/8 out in front. Let's put parentheses around this guy. So I've got 1/8 times our total area of 1 minus 3 is negative 2, plus 2 is 0, and then 0.5 and 1 make 1.5, or let's call that 3 halves. So 1/8 times 3 halves would give us 3/16. So that is the average y value of the function f of x on this interval. So if I clear off all of this, so the fact that we have positive average value means that more often than not, this function is positive in its value. So another way of thinking about it is more of the interval from -4 to 4 is spent above the x-axis than it is below the x-axis, okay? So 3/16 would be, actually let me use the line, right about here, about a quarter of the way through. So that represents the average value of y for this function across this interval. All right, now our next topic, another application or another way of interpreting the fundamental theorem of calculus is the idea of accumulation of change. So if you remember, when we find an antiderivative, what we're really finding is the function that came before a given derivative. So not every integral do we want to interpret it as the function inside is a derivative. Sometimes we just want to use that function's graph to find the area under it. But if we treat each of those equations as the derivative of something, then when I integrate that f prime function, it takes me back to the original f. Or if I start with f double prime and integrate, it takes me back to f prime, and so on. So if we combine our knowledge of what a derivative represents with the fundamental theorem of calculus, we get a pretty powerful application, and that is this accumulation of change. So suppose we have a function f of x that's continuous and differentiable on the interval a to b. First, we know that a derivative function represents the instantaneous rate of change for an original function or quantity. So f prime tells us how f of x is changing at any given moment in the interval a to b. Secondly, the fundamental theorem of calculus tells us that if I integrate f prime of x dx from a to b, its value, that integral, is equal to f of b minus f of a. So again, another way of interpreting this is the area under f prime of x equals that f of b minus f of a value. So just keep that in mind. So if f of b is equal to the value of f at the end of the interval, and f of a is equal to the value of f at the beginning of the interval, then their difference would represent the amount of change that f has occurring to it over the entire interval, or the total amount of change that accrues under f for that interval. So putting all of this together really tells us that the area under f prime represents the total amount of change in f of x over the interval a to b. And that is a really powerful connection and interpretation, and allows us to make all kinds of really, really helpful and important applications with this fundamental theorem of calculus. So from now on, when we see a function that represents some derivative f prime, when we see that its area is being calculated under it, this goes back to the units example at the very beginning of this section. If I have feet per second multiplied by second, that is why this area has units of feet, because whatever the end position is minus the beginning position, that difference tells us how much feet of change we have seen in the position of that object over the course of that interval. So this is the really big, important application of the fundamental theorem of calculus. So the formal name of this idea, this interpretation, is called the net change theorem. So the definite integral of the rate of change of a quantity, f prime, gives the total accumulation or net change of that quantity on the interval a to b. So the first way of writing it is the way that we've already seen it. The integral from a to b of f prime dx equals f of b minus f of a. But the power of the net change theorem is if I tell you where the quantity starts and you have its derivative, then we can use those two to figure out where do I end up. So another way of thinking about this, or a manipulation of the fundamental theorem of calculus, is to figure out where I end up, all I need to know is where do I start, plus then I need to find the total amount of change that occurred to f in that interval. So again, I can interpret that integral of f prime as the total amount of change in f. So if I want to know where I end up, give me a start value and its derivative, and we can use calculus to figure it out. Or another way of thinking about it is if you want to figure out what did you start with, then all I need to know is where did I end up, and instead of adding the amount of change, we would take it back. So we would subtract the total amount of change that we see occurring to f across that interval. Again, going back to the example of you being a cashier, at the beginning of your shift, you have a drawer full of money. At the end of your shift, hopefully you have a drawer with even more money in it. So if you had some formula, some equation to calculate the amount of change that happened during that shift, to know either how much you started with or how much you ended with, all you have to know is that in-between information. That is our derivative, and that's our calculus side of it. So if I tell you that you earned $700 during your shift, if you started with 200, then you know you ended up with 900. Or if you ended up with 900, you know that you must have started with 200. So mathematically, it's not that earth-shattering, but conceptually, this is a big deal. This is a theorem that we can apply to lots of different situations. So let's try a couple of these. So first one here says, a chemical flows into a storage tank at a rate of 180 plus 3t liters per minute at time t in minutes. So this guy right here, as soon as you hear the phrase rate or units that say something per something, that is your clue that this guy is our derivative. It's like our f prime. Now, notationally, we'll change it to whatever we need it to be, but this is the thing that calculates my change. And I know that because a rate is the same thing as a rate of change. So it's describing how the liters in this tank are changing as time changes. So every minute that passes, the amount of chemical that's in the tank is either increasing or decreasing by this rate. And now they give us an interval of time, so whereas time is between 0 and 60, so the first hour, 60 minutes. So what we want to do is we want to find the amount of chemical that flows into the tank during the first 20 minutes. That's the first piece of information. But then I also want to find out the amount of chemical in the tank at t equals 20, if possible, okay? So for the first part, if you want to find the amount of chemical that flows into the tank, so if you think about that question, so how much chemical has flowed into the tank during that interval? So if you think about possible answers to that, it's obviously going to be some kind of number, but if you think about the units involved, to answer the question, how much chemical has flowed into the tank, if I said 400 liters per second, that doesn't actually answer the question. Liters per second, or excuse me, liters per minute was the unit that was used here. Liters per minute is not an appropriate unit for this question. Liters per minute is describing the rate at which chemical is flowing into the tank, but it doesn't answer the question, how much chemical? How much would be simply liters. So it's important sometimes to think about the units of your answer, because that will kind of inform the process a little bit. So if you're stuck, think about the units involved, and then let's think about how we can create that unit with the information given to us. So again, what we have here is some function, 180 plus 3t. I know that's not what the graph looks like, but I like to just draw these generic graphs with this big rectangle. So again, if I have some graph and I want to estimate that area with one rectangle, and I think about the units involved, our rate of change function here, the y values would have units liters per minute, and then the input or the time variable is measured in minutes. So again, this area under whatever that curve looks like would be liters per minute times minutes, which cancels out and leaves us with just liters. So that is how we create the units that we need. We need to find the area under this function. So to answer this question, we just have to integrate from 0 to 20, because it's the first 20 minutes that we're looking at, for the function that represents this rate of change. So 180 plus 3t dt. So integral of 180 would be 180t, and then integral of 3t would be 3t squared over 2. We'll go 0 to 20. So my f of b, plugging 20 in, would give me 3600 plus 20 squared is 400, times 3 is 1200, divided by 2 is 600, and then minus 0 is our result for f of a. So we get a total of 4,200 liters of chemical. So that number represents the amount of new chemical that has flowed into the tank during the first 20 minutes. So if you think about all the relevant information here, the one big important thing that's missing is how much did we start with? If we don't know how much we started with or how much we ended with at the end of the 20 minutes, so the total amount that's in the tank, not just the new that's introduced, then we can't really answer we can't find the other missing piece. So just knowing the rate of change is not enough for us to either figure out the start or end values. We have to be able to know one of those if we want to find the other. So for the second part, it says find the amount of chemical, total amount of chemical in the tank at t equals 20 if possible. But in this case, it's just not. So what they would have to be able to do, or what they would have to provide us with to answer this would be, suppose the tank starts with 200 liters in the tank. So if at the start of this clock, when we actually turn the pump on or whatever, and new chemical starts being introduced into the tank, if there was already 200 liters in there at the end or at the beginning, now we could figure out how much total is actually in the tank after those first 20 minutes. So again, if here's my tank, if the water level was at 200, or the chemical level was at 200 liters when t equals 0, by the time t equals 20 minutes, now I know that there has been a new 4,200 liters added in there. So by the end of that, we know that the new total would be 4,400 liters. So again, this is the idea that if I want to know, sorry, went the wrong one. If I want to know my end value for some quantity, in this case, the amount of liters of chemical, then I have to know my starting value and then add to it the integral from a to b of that rate of change function. So I use the calculus, I use the integration and the fundamental theorem to find the total amount of change, or in this case, new chemical that has been introduced, and then I can add that on to the starting value to find our end value. So just be on the lookout for these. When you see problems that provide you with a rate of change and either a start or an end value, then that is a net change problem, and we want to set it up using one of these forms. Now, again, the first one is just our standard fundamental theorem of calculus. So for net change, it's actually going to be a choice between these two options, and it's just a matter of, are we looking for an end value at the end of an interval, or are we trying to work backwards and figure out what I started with at the beginning of the interval? Now, in certain situations, the net change theorem can be interpreted in an even slightly different way, and that just is based on what the functions represent. For example, if our function represents the velocity of an object, then remember, velocity is telling us the change in a object's position. So remember, that's the whole idea. V equals change in position. So if we integrate the velocity function, we're finding the total amount of change in that object's position. But velocity is a vector, so we have to always keep that in mind. Remember, it shows direction. So it's not just about how fast the object's moving, it's about what direction it's moving to. So because of that, we have two ways to interpret the result of integration, or the area under the graph of velocity. And it depends on which one we use, actually depends on which thing that we are trying to find. So the first one is called displacement. So displacement is just the change from the beginning to the end position. So suppose that I have a remote control airplane, and I start flying it, and it goes up and down. So let's say that it first releases from my hand at a height of 5 feet. And then over the course of time, I start flying the plane up and down. And when it lands, it comes back down to my hand, back at 5 feet again. Well, if that was the case, then this position graph would tell me that the total displacement of the object is actually 0. And that's because from the start to the end, there was no change in position of the object. At the beginning of the interval, it had a height of 5 feet. At the end of the interval, it had a height of 5 feet. So if I did integrate velocity, remember that takes me back to my position function. So that would be the position function's value at B minus the position value's function at A. So it's really just the net change in position. It doesn't account for all the changes that occurred in the middle, because when I move up, remember that is a positive velocity, and when I move down, that's a negative velocity. So what ends up happening on the graph of velocity is you've got positive area and negative areas that counter each other out. And sometimes, in this case, the exact same positive area would be matched by the exact same size area in the negative portion, so they would totally cancel each other out, giving you a displacement of 0. So displacement is just the idea of net change in regard to position. But that doesn't necessarily tell the whole picture of like what this airplane was doing. The airplane was moving up and down, and its position really was changing the whole time. But because you're integrating just regular velocity, and that has that vector, the direction aspect of the vector in there, it doesn't tell the full story. And so that is the difference between displacement and total distance traveled. So total distance traveled means I don't care what direction I was moving. I'm just tracking a speedometer or an odometer in my car the whole time. So it doesn't matter if I'm driving away from my house or towards my house. If I'm moving, I am calculating a total amount of distance that I have traveled that whole time. So in that aspect, what we have to do is we have to ignore the direction aspect of velocity. And to do that, we actually have to take the absolute value of the velocity function. So remember that if, in this case, for this example, if I really was going up and down, then I would have had positive velocity, and then negative velocity, and then positive velocity, and then a little bit more negative velocity. So it would have looked like something like that. But when I take the absolute value of any function's graph, remember it's a folding action. Any negative portions of the graph now become reflected up, and it actually creates those sharp turns. So these negative area regions would actually be flip-flopped up above this graph, so that all of the area then would be positive, so that when we total them all together, the negative and the positive don't cancel each other out anymore. It actually just all totals up to be the total distance that that object has traveled. So that's the tricky part. So when we want to find total distance travel, we have to do this to this function. We have to fold all the negatives up to make them positive, and then calculate the areas all together. All right, so let's try some of these. So for this first one, it says a particle is moving along a line so that its velocity is v of t equals t cubed minus 10t squared plus 29t minus 20 feet per second at time t. So for A, I want to know what is the displacement of the particle on the interval 1 to 5. So this is the easy one. Displacement's always easier because it's straightforward. So if I want displacement, I just want to know what is the difference between the position at the beginning and the position at the end. So to get that, I need to integrate. So displacement, I'm just going to call that d for right now, would be equal to the integral from 1 to 5 of my velocity function. So actually, just to save me a little bit of time, I don't need to rewrite the whole thing again. It's sitting up top, so I'm just going to use the name. So if I do that, I get s of 5 minus s of 1. Or actually, I'm sorry. Let's actually find the antiderivative here first. So let's integrate these four terms. So I get t to the fourth over 4 minus 10t cubed over 3 plus 29t squared over 2 minus 20t. And we're going to go from 1 to 5. Now, this would definitely be 1. You definitely want a calculator for this. In some of these, it's unavoidable just to speed up. There's no sense in making you guys struggle with all these calculations on and on and on. Especially when we have these terms with different denominators, it's just going to get a little obnoxious. So it's okay if we use a calculator to speed this up. So if I do that, when I plug 5 in and do all the simplifications here, we end up with 25/12 for that value. It comes out to be a decimal, but it's easier to start with fraction form. And then minus the starting position, if I plug 1 in here, we end up with negative 103/12. So subtracting the negative becomes plus plus. So we end up with 128 over 12, or 32 thirds. So 10.6 repeated. So what that number represents, it means that from the start of the interval to the end of the interval, this particle must have moved in a positive direction a total of 10.6 units. Now, that does not mean that the particle was always moving to the right the entire time. All it means is that no matter how it moved in between, from the start to the end, the net change was a total movement of 10.6 repeated units to the right. Or to visualize this, if this is my number line, here's 0. This is saying at the start of the interval when t equals 1, it was negative 103/12, which is like about negative 8.6. So this was my starting position. So this was where the particle was at t equals 1. Now again, in between there, until the end at t equals 5, that finishing position was at positive 2.08. So right here, or 25/12. So that is all that we know from this problem. But what we don't necessarily know is how we got here. I know where I started and where I ended up, but it doesn't tell the full picture of the particle moving left to right. It could even go past that and come back, but we know where it finished. The in-between, that is what we are going to figure out for part B when we look at total distance. All right, so now for part B, we're going to take a look at what is the total distance traveled by the particle on the interval. So again, imagine you're driving in your car and you're going all a bunch of different directions, but your odometer is constantly tracking the total distance that you've traveled. So when you leave your house, go to work, drive, go shopping, and then you end up back at your house, in that case, your displacement is 0 because you ended up where you started. But your total distance traveled is not. It would be the total distance that was measured or tracked by that odometer. So we're essentially going to do that for this particle now. Again, part A, displacement, discounted the fact that we could have possibly been going a whole bunch of different directions, and now and all we did was just look at the start to end values and that difference, but now we're going to take into account all those different changes. So first we need to set up the integral. So again, total distance traveled will be the integral from, let's see, our integral is 1 to 5, of the absolute value of v of t. Now again, I'm not going to put the whole big equation in there because we're going to do this a different way. So for you guys by hand, you would not actually be able to evaluate this by hand because you would have to know exactly what the graph looks like. You would have to know exactly what the x-intercepts are and know exactly what area to integrate separately and then change the sign for. That would be the idea of the negative area being reflected up and becoming positive. That's an insane amount of work. You would not actually be able to factor this guy by hand anyways, or excuse me, this guy by hand anyways. So we'd have to go through some really difficult math in order to be able to do that without the aid of a calculator. So with that in mind, I'm going to show you guys how we go about doing this kind of problem in the calculator. So your calculator does have the ability to do a lot of calculus for us, where we don't actually need to rely on doing everything by hand, okay? So first things first, I have a function that I'm going to integrate, and that's my velocity. So I'm going to put that guy in y equals, okay? So now again, we don't use t's in the calculator, so I'm going to have to use x's. So I'm going to do x to the third minus 10t squared plus 29t, or x in this case, and then minus 20, okay? Now, I'm going to look at the graph. We don't necessarily have to look at this graph to do this, but I do want to just kind of explain to you guys again what we're looking at. So again, our focus is on the interval from 1 to 5. So it actually looks like, and we can trace this guy. Let's trace and go to 1. That actually is an x-intercept. And it may actually look like these are actually nice, easy points. Maybe we got lucky here. So 4 and then 5. So those actually are the 3 intercepts. So that while this guy is not factorable, we would be able to use synthetic division to actually go through and solve those. So right now, this function from 1 to 5 has positive values, and then it has negative values. So anytime that this function has a positive value, again, that means the particle is moving to the right. So for that whole interval from 1 to 4, the particle is moving to the right. But then from 4 to 5, we have negative velocity values, which means it came to a stop and then turned around and started going back to the left. So all of that distance that we kind of backtracked on when we look at displacement got canceled out. So we did not account for that. So that is where we have to use the absolute value function, okay? Now, I do want to show you how we can make the calculator integrate functions for us. So we're going to get out of here, and I just actually want to repeat part A in the calculator. So our function is now stored in y1, but if we go to the math menu, on this menu, there are 2 options, calc options, down here. Number 8 allows us to take the derivative of a function and then evaluate it at a particular value of x. We've done that in the past. But then option 9 is the same thing, but the integral version. So newer calculators, your screen will look like mine right now. Older calculators, it just opened up a parentheses for you, and you're going to tell it 4 things. You're going to tell it, let me write this down for you. So if you have an older calculator, to do this problem in the calculator, your screen right now says fn int, and then an open parentheses. So you're going to tell it 4 things. What function is it that you want integrated? And our function is stored in y1. We could also, if we wanted to, we could type this guy into that spot in the calculator, but it's easier to put it in y1 and then call it up. And then comma, then we want to know what variable you're going to integrate with respect to. That is always x. and then we have to tell it the interval that we're integrating on, so 1, 5. So those are the 4 things on the older model calculators that you would have to enter. For the newer ones, you're going to still tell it those same 4 things, but we're actually going to fill in the actual interval. So we want to integrate from 1 to 5, and the function we're integrating is y1. If you remember to call that up, we go to vars, which stands for variables. We are working with y variables because of the y equals, and we're in function mode. That's the mode we're always in for right now. And then you just pick out where you put your equation, which is y1. So, whoops. And then our last spot, we just fill in dx, so we use the x button. So that's it. That is our expression. When you hit enter, we get the exact same value that we got by hand, okay? Now, I showed you that so that doing it for the new guy, or the next one, is a little bit easier, okay? Now, there are 2 ways to do this. One way is to create a new function. So I have y1 is my original velocity, but for our total distance traveled, I need to be able to integrate the absolute value of that function. Well, the absolute value function is under the math menu. If we go over to number, that very first option, absolute value, it actually brings up bars for the newer calculators. Older guys, it would say ABS open parentheses, and then you put y1 in there and close it. So for the newer ones, I'm going to go back to vars function, and I'm going to put y1 inside of those absolute value bars. So now when I go to my graph, you see the exact same thing, but now we reflected all of that negative stuff up above the x-axis. Now for us, this part that got reflected up doesn't mean anything to us because that's not important. It's outside of our interval. But from 1 to 4, I'm still positive, but now that negative area from 4 to 5 has now become positive. So now when I integrate for this function, now it's just going to accumulate all of that positive value so we don't cancel anything out. So now to do this, we're going to repeat this process, but I put my absolute value version in y2, so that'll be my function. So I'm going to go to math, option 9, from 1 to 5, and then vars, y-vars function, and I'm going to choose y2 this time with respect to x. And again, older calculator, same 4 spots. The only difference now is y2 instead of y1. And now we get a bigger number. We know it had to be bigger because there was some positive and negative stuff that canceled each other out before, but now it's all positive. So in this case, we end up with a total distance traveled of 11.83 repeated. Or if you want it in decimal, or excuse me, fraction form, we can go math, enter, enter, and we get 71/6, okay? So that is the idea. And again, we can evaluate, or we can use a calculator on the calculator active portion or any calculator active questions. We can use the calculator to do these problems. And again, in certain situations, you have to use a calculator. Like the next one coming up is another one that we're going to have to use the calculator for. But setting it up and understanding what it is that we have to do with our absolute value bars is super important for these kinds of problems. All right, let's take a look at another one of these. So another kind of net change minus. Again, the idea of displacement and total distance traveled, those are specific examples of net change relative to our particle motion stuff, okay? So for this next one, Mr. A is baking cookies for his favorite calculus class at a temperature of 350 degrees Fahrenheit. He then takes out the cookies and turns off the oven, and that's when the clock starts. So that corresponds to t equals 0 minutes. The temperature of the oven is changing at a rate of -110 times e to the negative 0.4 degrees Fahrenheit per minute. So that right there, so it first off, it says rate, but also the units here, degrees Fahrenheit per minute. That means that this guy is a derivative. Whatever you want to call it, let's say, just because we're using T as our input, let's call it O. So if O represents the temperature of the oven, then its derivative, O prime, will be the rate of change of the oven's temperature at time t. So what we want to know is, to the nearest degree, what is the temperature of the oven at t equals 5 minutes? So essentially, after 5 minutes have passed, what is now the temperature? So again, you were given two pieces of relevant information, a start value. So when the clock started, the temperature was 350. And then you were also given a rate of change function, a way to calculate how that initial value is changing. So that all put together spells out that this is a net change problem. So again, in this case, I'm setting up the variety of I want to know an end value, and that is equal to a start value plus that sum of change. And in this case, we're going to be looking at the sum of the oven's temperature. So my end value in this case is I want to know what's the oven temperature after 5 minutes, and that would be equal to the oven's temperature at the beginning. Now I'm just realizing that O and 0 looks very similar. Sorry about that. Plus the integral of O prime from 0 to 5. So that oven temperature's rate of change is our exponential function here, negative 110 e to the negative 0.4 t times dt. Now, for the time being, we do not yet know how to integrate a function that has a composition inside. So if this was e to the t power, then we know how to integrate that guy. But we have not yet learned the chain rule or u substitution for integrals. That is coming, but we're not there just yet. So because of that, this one has to be done with the calculator, okay? So let's pop over to the calculator. Actually, let's go ahead and set this up first. We are told that at the beginning, my starting temperature was 350, and then I'm going to calculate what this total amount of change is going to be, and then we can find our total. Okay, now to get this set up, though, we need to go back to y equals. Let's clear out y1 and y2. We don't have to worry about absolute value or anything this time. So this one is just our original function. So we've got negative 110 times e to the negative 0.4 t, or again, in this term, x power. So again, I don't always have to look at the graph. That's not relevant information to us right now. And actually, you know what? Let's do it anyways. Actually, that's not helpful. Sorry, I forgot the function's going to be gigantic. So let's ignore the graph right now. But now we set up our integral, so we're going to go math 9, going from 0 up to 5. Our function is stored in y1. Whoops, wrong arrow. And then with respect to x always. So we get negative 237.783. Negative 237.783. Just double check I wrote that down right. Okay, so again, that number represents the total amount of change that the oven's temperature went under during that interval. So what that means is whatever the temperature started out as, by the end of the interval, it had decreased 237.783 degrees Fahrenheit. So now that I know my starting value, I can combine these two to get the end temperature of the oven. So that comes out to be 112.217 degrees Fahrenheit. Now, if we really think about the units here, let's go back to this integral real quick. Again, this function that I was integrating, the other interpretation of this is the area under the graph of this exponential guy. Well, in this case, this guy is a negative exponential function, so it looks something like this, okay? So it's upside down and it's approaching 0. But from 0 to 5, that area represents the total amount of change that the oven's temperature went under. But our final units here is in just degrees Fahrenheit, and that's because the y direction for this function had units of degrees Fahrenheit per minute. And our x direction is being measured in minutes. And again, when I multiply those units together, this area ends up having a unit of just degrees Fahrenheit. Again, that's one weird part about these real-world area problems that you do have to get used to rather quickly to be able to fully understand them. We have to abandon the idea that area always has to be something squared. That's in geometric terms. But in real-world context with these calculus problems, because the functions their y values are a rate, so something per something, and the input matches that bottom unit always. That'll always be the case. It'll never be degrees Fahrenheit per minute, and then our input is measured in kilometers. The units always have to match up. That's one of the rules that we talked about with derivatives, is that the derivatives output units is always a ratio of the output and input units for the original function. So it's always going to be a y variable over x times the x variable, so they cancel, so we're only ever left with the y units of the original function. So that's why I know going into this unit is going to be degrees Fahrenheit, this answer's unit is going to be degrees Fahrenheit, which is how I know that the final answer will also have degrees Fahrenheit.